So, what we want to talk about today are properties of logs. We discussed what a log was yesterday. We're looking for an exponent when we're talking about a log. And so today we want to talk about some of the rules and properties for logs. And because logs are looking for an exponent, logs are equal to an exponent, they follow a lot of the same rules that exponents do. In fact, the laws of exponents have a direct relationship to logs. And so today we want to look at our properties of logs. So let's take a look at a couple of properties of logs. There's a couple of little ones that you just want to remember in general. Don't forget that when we are doing logs, we are looking for an exponent. So there's just a couple of general rules that just always happen. For example, any log could be any base. I don't care what the number is, 10, e, 20 million, 0.25, any base, any log of 1 is always equal to 0. And this is because anything to the 0 power is going to be equal to 1. Anything. So if I take 5 to the 0 power, I get 1. If I take a million to the 0 power, I get 1. If I take 0.25 to the 0 power, I get 1. So any log of 1 is always equal to 0. So that's something that you want to remember. Anytime you have a log of something that has an exponent, so log base a of a to the x power, okay? Anytime the base of the exponent and the base of the log match, they actually cancel each other out. And so all you're left with is the exponent. A to what power equals a to the x power? X. A to the x power equals a to the x power. So anytime your bases match, in essence, they basically cancel out. And so all you're left with is the exponent. That's important for when we're trying to solve equations. Another way to think about it is they are inverses of each other, exponents, an exponential, and a log, and so they would cancel each out very similarly to a square root and a square. And so that is a property that you want to remember. Anytime you have a log and the number you're taking the log of matches the base, that's always going to be equal to 1, because a to what power equals a? A to the first power equals a. And so those would be equal to each other. So these are just some very basic properties or ideas about logs that you want to keep in mind. When we generally talk about properties of logs, there are 3 basic laws of logs that you want to talk about that have to do with the laws of exponents, and we want to remember those, okay? One of those laws says that if I have a log of a times b, so this is what is inside my log. Again, it can be any log, not just the common log, but any log of a times b. We can actually break that up, and we can say that that's going to be equal to the log of just a plus the log of just b. Recall, if you multiply like bases, you add the exponents. So remember, this is always dealing with exponents. The log is equal to an exponent. So if these two things had the same base, which they do, because the log has the same base, when you're multiplying like bases, you are adding the exponents. So the exponent of a and the exponent of b would then get added. That's the exponents that we're looking for. So multiplication goes with addition. Now, the cool thing about this law is it works both ways. If I have 2 logs that have the same base that I'm adding, then that means that I am multiplying what's inside of them. So it does go both directions. Equal signs are very powerful. They mean that things are equal. So if multiplying like bases, we added the exponents, what should we do if we are dividing like bases? If you recall from laws of exponents, dividing like bases meant that you subtracted the exponents. So that one would give us subtraction. So we have log base a. So again, we could break that up either into subtraction, or if we have a subtraction problem, we can put it back together again as division. And the third one goes along with our power to a power rule. It says if I have a log of something to an exponent. Now in this case, the bases don't match. It's not just going to cancel out. But if I have any log of some number to an exponent, when you take a power to a power, what do you do with the exponents? You multiply the exponents. Well, this is one of the exponents. The other exponent is whatever log of a is. So when you take a power to a power, you can multiply the exponents. So in essence, this exponent that's up here moves up to the front of the log, and so that would be multiplying our exponents. So when you multiply like bases, you add the exponents. When you divide like bases, you subtract, and when you take a power to a power, you multiply. So just remember, a log is always equal to an exponent, and so that means it behaves like an exponent. These laws of logs, helps us to do two things. We can do what we call expand a logarithm, or we can condense. And folks, there are circumstances where we would want to do both of these things. Sometimes when we're trying to solve an equation, we have a variable and we're basically just trying to peel everything off of it. And so we like to expand it out so that we can kind of peel everything off of the x so that we can solve for it. Sometimes we just have multiple logs and we're trying to condense it down so that we just have one log to deal with. And so that's when we use condensing. There's situations that we will use both. But expanding is when I take a single log and I bust it up into a bunch of individual logs. Condensing is when I take a bunch of individual logs and I push it all together so that I just have one log. So for example, if I have the following problem and I want to condense it, that means I want to put it all back together. Let's say that I have 2 log x plus 3 log y minus 4 log z. Alright, so these are the things that we want to talk about. One of our laws of logs said that anytime we had something being multiplied by a log, that means it's a power times a power, an exponent times an exponent. That means we must have a power to a power, that this actually belongs up in the exponent of this thing right here. So that means that for all of these that have a number up front, we need to take that number and move it up to the exponent. So that's going to be the first thing that I do. So now I have log of x squared plus log of y cubed minus log of z to the 4th power. Now, we had rules that said that if we are adding two things, then we need to multiply whatever is inside the log. So these two are being added. Now notice, when I condense, I'm taking it to just one log. So I'm adding these two logs. They're going to become one log, and then I'm going to multiply what was inside of them. That would be x squared times y cubed. Now I still have my minus log z to the 4th out here, and so I have to remember that subtraction, when we subtracted, that meant that we divided whatever was inside of them. So when I do the subtraction here, I'm going to end up with one log, and x squared y cubed is on the top, and it's being divided by z to the 4th. So don't forget, when you are condensing, you are taking many logs and you are trying to put them all together into one single log. So it's what's inside that's being multiplied. It's what's inside that's being divided. We do just have one log. That would be an example of condensing. Expanding is when you take one log and you're trying to break it up into a whole bunch of little logs. So for example, if I have natural log of 4x squared over 3y to the 3rd, and I wanted to expand this problem, what I would have to realize is that I've got two things being divided here. What I generally do is I realize that anything on the top of a fraction inside of a log is going to end up in a positive log. Anything in the denominator, because it's dividing, should end up inside of a negative log. So there's really four things going on here. I have a 4, I have an x squared, I have a 3, and I have a y cubed. These are the three things that I need to break up inside of this log. So I'm going to end up with a positive log, natural log of 4, because it was on the top, plus a positive log of x squared, because it was on the top. 3 was in the bottom, so it's going to be minus the natural log of 3. Again, division becomes minus. That's what we had in our rule, is that anytime we were dividing, it ended up being in the negative log. All right. Y cubed is also in the bottom. We're dividing by y cubed, so it's going to end up with a minus here as well. Sometimes at this point you're done, but in this problem I do notice I have some exponents, and we know that exponents can move up to the front. So when I move these exponents up to the front, I have natural log of 4 plus 2 natural log of x minus natural log of 3 minus 3 natural log of y. You aren't done until you only have one single item inside of each log. At this point, that's as broken down as that's going to get, and that would be my expanded answer.